So hi, yeah, my name is Ivan Skorokhodov, and in this talk, I will talk about our uh, paper, which is called Aligning Latent and Image Spaces to Connect the Unconnectable, and it is about infinite image generation. So a little bit about the contents of the talk. So first, I would like to say something about coordinates conditioning. Um, it which is used in modern models, and then because it is like a preface for our work, since we heavily rely on the coordinates information during the generation process. Okay, so the coordinates conditioning. One of the earliest work that used coordinates somehow inside a neural network was CoordConv paper, and they proposed to replace a normal convolutional layer with a convolutional layer with concatenated coordinates to it. So we have some hidden representation, and we concatenate to channel-wise. We concatenate some coordinates coordinates positions of each pixel. And then we apply our convolution. So instead of having a representation of C channels, we have C+2 channels now. And I suppose that the question is, why do we need this? So in the original paper, they showed that it improves the performance on on the tasks which somehow incorporate somehow require the predicting the location positions. For example, object detections or some far-fetched problems like regressing a pixel coordinate or something like this. But for GANs, it turned out that using coord-conf layers creates interesting side effects. So the one side effect that the paper explored was geometric translations during interpolation process. So we have two images and two samples from a GAN model, and we want to interpolate between them. And if your generator employs this kind of layer, coord-conf layer, then these interpolations, they look more similar to coordinates, to geometric translations. So just by adding, simply by adding this coordinates information. So feel free to ask questions along the way if you want. So is this part clear? Because it will be like important for the subsequent talk, subsequent slides. Okay, and a simple extension to this coord-conf layer was Patchwise GANs, Coco GAN, coordinates conditioned GAN, and they built a generator which produces an image patch by patch. And each patch is generated independently. So we have some a latent code. We repeat it specially and concatenate some coordinates information to this code. Then we feed it to the generator, and the generator produce patches of the image, which is described by this latent code. And the main struggle or the main difficulty of this approach is how to merge the patches together. So, because if you generate patches independently, then they will likely have seams between them. So there will be too sharp transition between between the patches. But it turned out that adding these coordinates information is enough to make the generator learn how to merge the patches itself on its own without any additional mechanisms. So it is an interesting observation, and it was used in several um, subsequent works. And for example, Alice, also our work, we also use Patchwise generation. So, and now I would like to talk a bit about Inarguance, since Einar-based GANs. So an even further development of patchwise coordinate-based generation is Einar-GAN. So typically, images are represented as 2D array of RGB pixels. So we have an image, and this means that we have 3 RGB pixel arrays. But recently, there was another paradigm appeared, which proposes to represent an image as a neural network. So we have some coordinates grid, and we say that an image is defined on this coordinates grid. We pass some coordinate to the neural network, to the INR model, and it produces the RGB value in this coordinate. And we can reconstruct the original pixel-based representation from this neural network by evaluating it in all the coordinates locations. So in this way, a single neural network corresponds to a single image. There were several, so actually such paradigm is more popular in 3D deep learning for representing scenes, because it provides compression, and it provides a compressed representation of a scene, which is also useful, which is easier to manipulate with. But for 2D, there are also some interesting properties of such a representation. And having such representation, it becomes very tempting to build a GAN model which generates images in this form. And actually, there are several works that do this, and they all assume that your generator is partially, or is a hyper network, at least partially. So a hyper network is such a neural network which produces parameters for another neural network. And in case of Einar-based GANs, we have a generator that generates parameters for an Einar model. And this Einar model, it parameterizes some image. So, but how to illustrate this, consider a convolutional generator, a traditional convolutional generator. We have some input noise, which is passed into the convolutional through a sequence of convolutional blocks plus upsampling and activations, and this gives us an image. In case of Einar-based generator, we have some input noise which is passed through an MLP, and this MLP outputs a parameter vector. Then this parameter vector is plugged into another MLP, into an Einar model, and then we evaluate this Einar model in pixel on some coordinates grid to generate an image, a pixel-based representation of an image. And there are several interesting properties of such kind of GANs. For example, upsampling. So they can do out of the box upsampling by you can evaluate after you generated this parameter vector and plugged it into the INR, you can evaluate it on a much finer, much more detailed grid. So actually you can evaluate this model in any coordinates location. And this gives you an image of much higher resolution than you used at train time. And there is an interesting property which actually motivated our work, which is called image extrapolation. So as I said before, you can evaluate your INR at any coordinates location, and it was observed that um, it was observed that they can extrapolate to novel coordinates locations. And this gives you a mechanism to do image extrapolation for fake images by evaluating the INR model at outside of the coordinates grid that was used at train time. So if at train time we were generating images in the position uh, from 0 to 1, for example, uh, at test time we can try to generate to compute pixels at locations outside of this train time grid, and this to some extent provides meaningful extrapolation. But extrapolation is limited, and as you can see from these samples, for example, it cannot extrapolate further vertically. And also horizontally, it starts suffering from artifacts. And in our work, we tried to develop this property, this extrapolation property, to the extreme. So yes, aligning. Our work is called aligning latent and image spaces. But first, I would like to talk about the common way of doing infinite image generation. So previous works, they generated infinite images they used infinite generation only for texture generation. And this um, this is achieved by using chord conv layers with periodic positional embeddings. So to generate infinite textures, it is enough just to make your generator periodic. So at some point, it can start repeat itself, and this does not create a problem for textures because this is usually what people want. Or if the period is if the period is large enough, then it is not noticeable. And yeah, as I said, you just use periodic coordinate embeddings. So what does it mean? To make the generator periodic, you use chord conv layer with with coordinates that are passed through some periodic function. Usually people use sine function. So if previously we were concatenating just raw coordinates to our hidden representations, then for periodic generator, we pass it through some periodic function. So this xy is a pixel location on the coordinates grid, and we compute the embedding the positional embedding of this pixel by multiplying its coordinates on some matrix and passing the resulted values through sign function. So sign is applied element-wise here. So matrix W is called a positional encoding matrix, and the resulting so the further mechanism works exactly like chord conv layer, and you just concatenate such embeddings to your hidden representations, to your 3D tensors, and apply your convolutional layer. And this results actually in it is a better alternative to the chord conv layer, especially for texture generation, because it adds periodicity, and for infinite image generation, we do not. So when we do infinite generation, then x, y at some point they become either too big or too. I mean, we'll have too large magnitude, and this will disrupt the model because we cannot generalize infinitely. But if our coordinates conditioning is periodic, then the model, the range of coordinates embedding is always suitable for our model. So, but this texture generator, so just simply extending this idea. So this idea works well for texture generation when there is not much content, or this content is this repetitive. It is fine for us to see the repetitive content, but for infinite image generation, this creates a problem because having repetitive content for normal images produces unplausible results. So it is not interesting to see infinitely repeating images of the same which are semantically the same. For example, here you can see that this panorama, it starts to repeat itself. So this is an attempt to use old texture generators to generate infinite images of some on more complex datasets. So here, so it starts repeating itself when so it has some periodic coordinates embeddings, and each dimension in this embedding, it represents a wave of different frequencies, and when the largest when the longest period finishes the circle, then the model starts repeating its generations. So for example, here it is the longest period has this size. For this image, for the second experiment, it is a bit larger, but anyway, at some point it starts repeating itself, which is undesirable. And we solve this problem. So this problem, it arises from the fact that all these images, that this whole infinite image is generated from a single global latent code. And in our work, we propose a solution how to generate an infinite image from different latent codes. We actually use infinitely many latent codes to generate an infinite image. So I have no idea why this video is green. So at some point it catches the color, the color for it. But so here is the teaser for the method. So how do we use infinitely many latent codes for the generation process? We first say that latent codes are located on the coordinates grid. So this is the main idea. So previously we were saying that only pixels are located on the coordinates plane, and latent codes, they live in some separate space. But in our work, we say that let's put the latent codes, let's bind them to the same coordinates plane. In this case, we use only one-dimensional coordinates plane because we consider only horizontal infinite generation. And we say that each pixel, it has a separate latent code, which is computed as the interpolation between anchors. So we first sample anchor latent codes and put them on the coordinates grid. And then we say that a latent code in position X, it is computed as the linear interpolation between the closest anchors. And this idea, when you try to implement it in practice, especially on top of the StyleGAN architecture, you encounter a problem because it uses an add-in so the first StyleGAN uses adaptive instance normalization to input latent codes into the generator. StyleGAN 2 modifies this algorithm a bit, but in general, this all is based on it is all based on the adaptive instance normalization, which works the following way. You have some so this is a decoder branch, and you want to input your latent code. You want to condition your latent code on the on the latent code. You want to condition your decoder on the latent code. For this, you simply project at some stage of the forward pass. You take your latent code, project it with a linear projection into the vector gamma and multiply it. Multiply it onto your hidden representation. And we modified this mechanism to make it work with this scheme. So what we did is as I said previously, each latent code is computed as the interpolation between nearby anchors. And imagine that we want to generate the following, that we are generating an image in this coordinates location. So we have some infinite infinite plane. We again consider the one-dimensional case, and we are generating an image, a frame at this location. This means that for each pixel, we need to compute the corresponding latent code, and we compute it as a linear interpolation between nearby anchors. So we sample three latent codes, project them linearly into vectors gamma, and compute the linear interpolations for each pixel. After that, we multiply them and a hidden representation during the forward pass. Also, our generator, it uses patchwise generation just as Coco again, and it is used to make the generator learn how to merge nearby frames. So because during training we generate a single frame, but we wanted which each during training frames generated. So we produce a single frame during the forward pass, but at test time we would like to generate frames one by one, and we want them to be stacked seamlessly with one another. So we want to avoid sharp transitions at these areas, and to force the generator on how to do this, how to avoid seams. We make the generation patchwise, and this gives an interesting side effect, which is called equivalence to shifts, which means that when you shift an input, your output shifts accordingly, typically by the same value. So what this means, imagine that we generated such kind of an image, and then we shifted the coordinates by 1/2, and the output becomes shifted accordingly. So if we compute the pixel values at the same locations, then they will be equal between one another. If we shift once again and compute the value in some different location, it will also be the same for both generations. Okay, so here are some samples from our model. We tried it on different datasets, and what is interesting is that it worked to some extent even on Elsan bedrooms. I'm not sure if you're familiar with this dataset, but it is like a very annoying dataset for infinite image generation, because its images from this dataset, they have they are not translationally like equivalent. So given to um, given two images of the same bedroom, there is you cannot transition. So you cannot transition between scenes in this dataset, because you have some walls which block the transition, walls or closets or something like this, which block the natural transition. But anyway, our method somehow managed to get it, and to some extent, so it has much more artifacts than landscapes generation, but still it works. And there are some limitations. So the main one is that image quality is lower than non-infinite generation. If you just train a stale GAN on the same dataset, then the image quality will be much higher. And another problem is that it learned to ignore spatial noise. And this spatial noise was actually, it is often used by people to embed, for example, to embed images in the style again. Another thing is that I noticed that truncation trick also does not work well for Alice, but I'm not sure why this happens. So it learned to ignore special noise because of Patchwise generation, but I'm not sure why truncation trick does not provide much improvement. And likely because we spent like interpolation properties of the generator on transitioning between scenes, like this connecting the unconnectable scenes. So we use the image interpolation. Sorry, we use latent codes interpolation for different purposes. And since style gain truncation trick is based on latent code interpolation, it does not provide the improvement. And also the model has some artifacts. The most common one are repetition artifacts. So since we use periodic positional embeddings, our image generations are also sometimes periodic. And another artifact is that sometimes we try to connect two unrelated scenes. For example, here we try to connect some water with faraway mountains. Here we will try to connect some waterfall, I think, with the tree. I am not sure what this is. And this creates, so this doesn't lead to anything good. This problem is solvable by doing some kind of clustering in the latent space. So trying to not to avoid connecting water, like trying to separate water latent codes and mountains latent codes, but simple clustering didn't work too well. And another limitation is that patchwise generation, it actually decreases the performance because generator, it is just, it becomes simply harder to generate images because you also need to learn how to merge them. Okay, so to conclude, coordinate conditioning is actually a general mechanism which is used in other areas in NLP, for example, as well in transformers, convolutional based sequence to sequence models. And INRs, they are mainly used, as I said, in 3D deep learning to represent 3D scenes. But there are applications, there are interesting in applications in 2D computer vision as well. And the overall idea of positioning latent codes into the coordinate space, it is popular in 3D deep learning as well. So in some sense, we brought a lot of ideas from 3D. And yeah, I think it is not, it is a remark that infinite image generation, it is not a big area. And for me, this, so I was working on this project more for fun. And it's not clear what application would make the project, this area would make the infinite image generation to become a big area. Okay, thanks. Thank you for your attention.